there are two classes of genuine entanglement. I mean W class and
G at Z.
Is there any bias towards them?
Certainly. I mean, G at Z would be, because that's the generic class. So G at Z is where, so in fact, this is the concurrence, so that's the entanglement between two qubits.
Yeah.
You can see that it's initially increasing in time and then it's decreasing. This is the tangle, the 3 tangle, which is the entanglement between the 3 qubits. G at Z states is a maximum.
Mm-hmm.
You can see that it's growing, and you can see that actually it's, where this is decreasing, that is growing. So this is the kind of monogamy that I was talking about. But in terms of W versus G at Z, W is strictly tangle is 0, right? I mean, the 3 tangle is 0.
Yeah, its volume also very, maybe 0 also.
Sorry?
Its volume on the state space.
Yeah, exactly. Yeah. So they're not generic. You would
but I was thinking that at least in W state, 2 qubits are somewhat entangled.
Yes.
That is remained. But it does not work.
No, it actually comes down the 2 qubit thing, and this is only for 3. So if you go beyond 6 qubits, typically there's no concurrence.
Oh.
It would just go to 0. It's exponentially small.
Again, in this I have a slight confusion. You said you're looking at 3 qubits and J equal to a 3 by 2 spin. You can interpret it as a 3 by 2 system. Now this 3 qubits, the connection between the two involves symmetrization of 3 qubit states. But the moment you symmetrize the space, the Hilbert space structure is lost, the tensor product structure is lost. So what is meaning of entanglement here?
This is the entanglement between the qubits. So, so this is what I'm talking. So at this level, you can't talk about this one large 3/2 spin, right? But you can think about it as being made of. So in fact, experimentally, that's what they're doing. Experimentally, they have 3 transmons, 3 spin half.
Okay.
So now, in fact, that is interesting. We have also further studies, because experimentally, to construct this, you need to have perfect interactions between them. They have to be permutation symmetric.
Yes.
So what will happen if that's not the case? That's interesting, because there you have a breaking of permutation symmetry.
I have an elementary question. Like, do we have a mathematical definition for measure of multipartite entanglement, like von Neumann entropy for bipartite?
Entanglement is this elephant, which in multipartite case depends on where you're, tapping it. So even bipartite entanglement between 2 parts of multipartite system, that is called the block entropy, which is studied mostly in many particle physics, is already some kind of multipartite entanglement measure. But that's telling you some particular aspect of entanglement. It's telling you how L by 2 qubits are entangled with the other L by 2, but it depends on the kind of question that you want to ask. For example, this concurrence, which I told you, is the entanglement between 2 qubits. Now you can enlarge your question and ask, what is the entanglement of L of those particles with M of those particles, where L plus M is not the total number. You have to invoke things like a partial transpose and negativity and so on. And there are interesting results concerning those in these cases. So
one more thing. You talked about monogamy.
Yes.
So is there any clear mathematical statement of monogamy in terms of these measures?
Yes, there are, especially for tripartite. You'll have some inequalities which are this tangle which I mentioned, the 3 tangle. All of that is coming from a measure of monogamy. It's basically how much entanglement. If you have A, B, C, you can talk about how A is entangled with B and C together versus how A is entangled with B and A is entangled with C. So you can.
Yeah, for the basic thing I kind of understand, but for multipartite, do we have a?
There are, so in multipartite cases, it's not as if there is, as I said, there is no consensus on, let's say, what is the most entangled multipartite states. We have studied a class of states called absolutely maximally entangled states, which just means that any bipartition you take of this multipartite state, it will be maximally entangled, any bipartition. But is that, and that need not exist also. For 4 qubits, they don't exist, for example. So, but even that, it's, and then there is geometric measures. What is the closest fully separable state? It depends on the task you want, and sometimes from a kind of operational point of view, one would ask what is the task which you want to do with that state, and what is the entanglement which is your quantity, which is your resource. It need not be even entanglement. There are other resources.
Thank you.
Yeah.
In one of those slides, you were comparing the dynamical evolution in the phase space density and in quantum mechanics.
Yeah.
So, keeping that in mind, how do you define sensitivity to initial conditions, like equivalent of Lyapunov exponent, purely referring to quantum dynamics without involving classical dynamics?
So there are, like for instance, you could look at very short times, and then you could look at some distance between states. People have done that kind of thing, but I'm not very comfortable with those things, because a Lyapunov exponent classically is really an infinite time element. Yeah. So it doesn't exist. That way there is no exact correspondence. The more modern approach, where people have kind of defined these Lyapunov exponents, is through this thing which I didn't skipped about, which is the growth of, if you look at a Poisson brackets, classical Poisson bracket of position at time t with momentum at time 0, then that is exactly given by the square of that is given, is telling you how much the trajectory at time t is differing as a function of x0. So that gives you an exponential growth classically. So people have studied quantities like these, which is basically the growth of the norm of commutators with time, and they find, not very surprisingly, that in cases where there is classical quantum correspondence, this quantity has an initial growth which is exponential in time, and in some cases it will match with the classical Lyapunov exponent. Again, it's not infinite time quantities, these are finite short time quantities, but nevertheless interesting. But I should say that even in spin systems like those or even circuits like what I showed you, nobody has found a positive Lyapunov exponent defined this way, although it's chaotic in other senses. So I would say that that's kind of open, but I would like to explore more the classical aspect via the Hilbert space formalism to get an idea of that.
I just wanted to bring to there was a paper, beautiful paper by Giorgio Parisi,
Yeah.
was trying to define what is n-partite entanglement
Yeah.
when n becomes large.
Yeah.
He showed it becomes like a spin glass problem, complexity problem.
Yes.
So
Yeah.
there was a question, so
Yes.
as n becomes larger, it becomes really apparent many ways of defining entanglement, as you said.
Right. Right.
So it's mathematically, Parisi has shown it's equivalent to spin glass problem with ultrametricity structures and so on. Thank you.
Yeah, it's a fascinating topic. Thanks.
Okay, so now we can go for coffee break and we reconvene at 4.
Thank you.
Thanks, Professor Ravi.
in the pocket glitch into it. Okay, great. Thank you. I know, but I only need delta t. So, yeah. Yeah.
Hello everyone. So next speaker, before I actually say about next speaker, there are a few announcements. So people who are in YouTube, you can type your questions and ask, and whoever is present here, you also feel free to ask questions in between. Okay. Then there was another thing. Okay. Please switch off your mobile or put it in flight mode or whatever, so that it doesn't disturb the lecture. Okay. So our next speaker is Professor Entanglement. He is a faculty member and was the chair of Center for High Energy Physics at IISc. He's an expert in particle physics, field theory, low energy effective field theories, supersymmetric models, and also some mathematical applications of behavior of Feynman integrals, etc. He's going to talk about particle physics phenomena and quantum mechanics. He's going to give a board lecture. So, board lecture, and yeah, his notes will be circulated after the lecture. Over to you, Professor.
Yeah, thank you very much. A very kind invitation. For me, Madras is always a home away from home, and especially IMSC. And I'd like to begin by thanking Sibasi, Ravi, and all the other organizers for inviting me here. I mean, it's like totally perfect organization and hospitality. And in fact, I've noticed that there's only one glass of water per speaker. So that kind of limits how much one can say. 4 speakers and 4 glasses of water. When I received this invitation, I had to think quite a bit about how to frame this particular lecture, because it gave a scope and aims for this workshop, including, making ideas accessible to MSc level students as well as teachers, educators, and also basically to members of the institute who are not subject matter experts. So I have to be able to say something so that everybody can take away something and it's of value to everybody. But I was also glad to see that in many of the opening remarks, both from Ravi and Simon, there were many comments made which makes my task somewhat easier. And then you will see as I go along how some of the things that I'm going to say are going to fit into the mandate of this particular workshop. Actually, it's kind of always very special for me to be here, because my late mother was first cousin of the founder of this institute, and few years before the founding of this institute, she was a young girl, and she would be at the residence of her famous uncle, a famous cousin, and she told me only just before she passed away that she had met Paul Dirac and had actually spent a fair amount of time getting to know him, which must have been quite a feat because he was well known for being particularly reticent. So anyway, I'm going to start today by many simple examples, and I'll build up the plot for you. Many things that you probably already know, but probably at the end of this lecture, it may give you a different perspective on what it is that I'm talking about. Okay? So, since this is to celebrate the 100th year of quantum mechanics, there's no better place to start than the Schrödinger equation. So let me do that. Let me look at the Schrödinger equation, one-dimensional system for a very special potential, which is the delta function potential. And let me take alpha greater than 0, which means that it's an attractive potential. And this is an example that every student does in MSc, and those of you who are in the audience have either taken it in the class or you have taught this. And then let's write this down, delta of x, psi equals e psi. And let's ask ourselves if there is a solution for e less than 0. which is a bound state, of course. We all know this. And from time to time, I may ask you a question, because I want to make sure that, that there's not a long, monotonous lecture, that there's a little bit of audience participation. I guess I can't ask him, but can someone tell me if there is a bound state solution, a bound state solution, many bound state solution? And I'll give you an answer. There's only one bound state solution, and this is given by psi of x, and this is square root of m alpha by h bar e to the minus m alpha mod x divided by h bar squared. And you can look at this and see that if you look at psi squared dx, it will converge and it will give an answer equal to 1. It's a very straightforward integration, and this is e is minus m alpha squared to h bar squared. So you may think that this is a textbook example, good for nothing. But let me give you an example of a real physical system where this actually has a manifestation. And now I consider a spherical square well, 3 dimensions, 3D, and then I write down the potential, which is spherically symmetric, minus V naught for r less than r, and equals 0 for r greater than r. So if we write this, then draw the potential, it looks something like this over here, fairly deep. And so from this example, you might imagine that there are some bound states, but it will turn out that if this well is sufficiently deep, there's actually only one bound state. And not only that, that bound state is going to be fairly close to the continuum, and it will be over here, like this. Now in this case, of course, the well is infinitely deep, so no matter how finite it is, it's pretty close to the continuum in this case. But in this, what I'm going to argue is a realistic example. It's going to look like this, and I'm going to ask you, what is the system that we are trying to model over here, where you know that a system has only one bound state. It's a realistic, real-life system. Now, I'll answer this for you, and I'll write down the radial part of the Schrödinger equation in this way, minus h bar squared du dr squared plus v of r u of r equals e of r. So e times u of r. So this is obviously for L equals 0, and this u here is equal to u of r by r is the radial part. Now there's a choice of parameters of this particular potential, where this is 2.1 femtometer and this depth is of the order of 35 MeV. And now somebody has to tell me what this bound state is and what this energy is and what is this physical system. Anybody, somebody, nobody? Okay, nobody. So this is 2.2 MeV. So you see this well is very deep, but this bound state is only 2.2 MeV. And now somebody can tell me what this is. This is a model for the deuteron. Deuteron is a system having one proton and one neutron, like so, and it forms a bound state with a binding energy per nucleon of only 1.1 MeV. Okay? Now, this is a very simple system where I have built up a nuclide known as a deuteron, which is made up of a single proton and a single neutron. And today we know that each of these is a spin-half fermion, spin-half fermion. So unlike in the example given by Simon this morning, you can't say one or the other because they are distinct particles. Okay? So this is such a simple system there where we are not yet having problems of having identical particles and doing statistics and so on and so forth. Okay? So here is a beautiful example like this. Each of them is a spin-half fermion. And then this has a spin, the deuteron has a spin of 1, and its orbital angular momentum actually has an admixture of L equals 0, which is about 96%, and L equals 2, which is about 4%. And how do we know all this is true? Well, you can measure the octopole moment of this thing, and then that will convince you that it must have an L equals 2 component. Okay? So I'm trying to build up a plot for you of how simple examples can be used to illustrate principles of quantum mechanics. So this is where we are with two distinct particles, and we have already made up a system out of this. What's the next simplest nuclide that you can think of? Well, you can think of, say, a triton. Triton has 1 proton and 2 neutrons. Or you can think of 3 helium, which has 2 protons and 1 neutron. And in fact, a triton is radioactive and decays through something that is known as the beta decay, to which we will get to after a little while, of which 3 helium goes to 3 helium, 3 hydrogen goes to 3 helium, with the emission of an electron and an antineutrino, and this is an example of beta decay, as I just said. But there are 1 or 2 more things that I want to point out about this particular thing, and I want to say that each of these, even though it's a spin half particle, is composite. How do I know it's composite? And later, what are the constituents of these protons and neutrons that we'll have to deal with? Now, all of you have studied in your MSc courses that the constituents of protons and neutrons are quarks. But how do we establish the existence of protons, of the constituents of protons and neutrons, from the point of view of basic building blocks such as identical particles, Fermi statistics, Pauli exclusion? That's going to be the basic mandate of my talk. I want to tell you that there are 2 properties associated with this. This is known as the Landé-G factor of the neutron, which is minus 3.82, and the Landé-G factor of the proton is 5.58. Often you will see numbers minus 1.91 and 2.79, which is 1/2 of this. Okay, one has to be careful with factors of 2, and then it turns out that the mu of the deuteron actually adds up very nicely and is just 0.879 times mu of the nucleon. So this is the prediction if you just add up these things, and you're in a position to add up these things because this is a very simple system. 2 distinct particles, so maybe their quantum numbers just add up very nicely, and it's true that it almost adds up to the actual experimental value, which is 0.857 approximately. Okay. Of course, it's not exact because there are interactions between the 2 which ruins this relation, but it's a pretty good approximation. Okay. Then you may want to argue that from the individual magnetic moments of the quarks, you may be able to obtain the magnetic moment of the proton and the neutron, and those are all exercises that we are going to be doing in the course of this hour. Everything here is simple, just things for you all to think about. So I can say that so far life has been simple. Does anybody agree or disagree with what I'm saying? Anybody? Yeah. So what happens if you have, so spin is easy to handle in such a simple case when you have distinct particles. What about more complicated systems? Then what happens? More complicated systems. I'm sure you have to struggle with these in your homework problems as you do them, but still it's easy to distance, or it is useful to distance yourself and ask yourself whether you can think about these things from a very elementary point of view, which is the aim of today's discussion. So, we are going to say that nucleons themselves, nucleons are composite, as we will see. That is, a proton is made up of 2 U quarks and a D quark. The proton has a charge of +1, so this has a charge of 2/3, 2/3, and -1/3. And neutron has a U, a D, and a D, where this has a charge of 0, so this is 2/3, -1/3, -1/3. Now, the mass of a neutron is very close to the mass of a proton. In fact, they are so close that despite the presence of the beta decay and the weak interactions which are responsible for the beta decay, the neutron decays rather slowly into a proton. Okay? So that's because the neutron and proton masses are very close to one another, and they are of the order of 938 point something MeV and 939 point something MeV, which means that the mass difference is very small. So this means that perhaps there is a symmetry that relates the u and the d quark, and the proton looks exactly like a neutron up to a swap between the u and the d quark. And this was an idea that was introduced by Heisenberg, the man whose work we are celebrating today, 1925 paper, but it was around 1931 or so, I think, he introduced the idea of what he called isospin in the strong interactions to explain this relationship between the u and d quarks, and to try to understand the nature of larger nuclides that you could build for protons and neutrons, trying to relate them to each other through swaps of protons and neutrons. Okay? He didn't know about quarks. His isospin symmetry was between protons and neutrons, and that was a isospin half representation plus half minus half, later extended after pions were discovered to pion triplets and so on. Today now we understand that this symmetry is actually enjoyed at the quark level itself, which is very nice. Okay? But while we are saying this, let me also say that there are other quarks. For instance, there is something known as the S quark, which is significantly heavier than the mass of heavier than the u and d quarks. And in fact, you can build up something known as the lambda meson, which also has 0, which has a u, d, and an s. Okay? Now this S quark is a much heavier cousin of the u and d quarks, in fact of the d quark, and but for the weak interactions it would also be stable, and you could in principle build up matter with lambda particles, lambda nucleons, hypernuclei as they are called. And this is a very useful thing for us to try to test notions of, let us say, of Pauli exclusion principle. But before that, I want to introduce you to one more quantum mechanics problem, which is again a bit of a surprise, because quantum mechanics was introduced to study radiation and atomic physics, to look at transitions among various atomic states, and second quantization, which was introduced by Jordan and some others, forgotten who, Jordan and somebody else, Fock and others had introduced it in order to explain radiation and the interaction of atoms with radiation. Now in 1928 already, please see the causation, आप chronology समझिए, as our home minister would say. It was very soon after 1925, 1928, Gamow already had a theory of something else, not beta decay, but something known as alpha decay. Somebody remind me, what is an alpha particle? Alpha particle, anybody? I already mentioned a triton, I already mentioned 3 helium. What comes after 3 helium? Quick. Mr. Red t-shirt, yeah. Helium, which is 4 helium, which has 2 neutrons and 2 protons. And the great thing about the helium nucleus is that it has a very large binding energy per nucleon. Please tell me how much it is. Very large binding energy per nucleon of about 7 MeV. Now this should surprise you, because I had already introduced a scale in the problem, which was a binding energy per nucleon in deuteron, which was just 1.1 MeV. This is about 7 MeV, which means that it's extremely tightly bound, and therefore it's energetically favorable for large nuclides to break up into daughters with an alpha emission. Okay? But then you need a theory for how such an alpha particle is emitted by this, and already in 1928 Gamow and some others, I see the names of Gurney and Condon, who gave a theory for this, and then they said, look, maybe there's a potential like this over here, and you can have an alpha particle in an effective potential like this, which rattles in and out, and if you have a state over here, then it can tunnel out like so. Okay? So large nuclei, very large ones, are unstable against alpha emission, and this is because of this particular property, that this thing is very tightly bound. Now this is an example of something that's known as an even nucleus, that is both the number of protons as well as the number of protons are both even. Okay? Now this is another fact, that the ground state of all even nuclei, ground state of all even nuclei nuclei, they have a JP, which is spin and parity of 0 plus. I don't think even today anybody really knows how to start with, from fundamental principles and get this result. It's a pretty amazing thing. What I'm trying to emphasize to our students is that you have all these universal properties of physical systems around us, which are very complicated, very complex, large numbers of protons, neutrons, you put them together, you create a complicated system. Still, there are properties which are very simple, okay? So this Gauss theory, now think about it. This was introduced for atomic physics, but it's being applied to nuclear physics, where the scales are MeV, several MeV, whereas atomic physics is a 13.6 eV, okay? That's the hydrogen ionization potential. So you're talking about phenomena which are 6 orders of magnitude away, which is the same theory that was applied and proved to be successful, at least to explain one of the well-known laws, which was in this plot, which is the energy emitted by this outgoing alpha particle and the corresponding half-life, log T half, and this always fell in essential straight lines, which actually was predicted by this theory of gamma of tunneling, where he also had a model for probability of emission, probability of emission. Together, they gave something known as the Geiger-Nuttall law. And this law holds over lifetimes, starting from milliseconds all the way to order of about 10 to the 20 life seconds, which is almost like the lifetime of the universe. So just think about it. Go back to the year 1928 and think how amazing such a result may have been at that particular time, that you could get a universal theory like this based on something so simple. Okay? As I said, alpha decay is not the only kind of decay, but the other more fundamental. So this is not a basic decay. This is an effective theory of unstable nuclei, but beta decay is caused by the weak interactions and the fundamental or basic beta decay is the decay of a proton into an E minus plus a nu E bar, and this, the energy of the electron emitted versus the number of electrons turns out to be some curve like this in general. This could be, a nucleus 1 going to a nucleus 2 plus E minus plus nu E bar. But you can also get so-called beta plus decay, and I'm not going to talk about that. So this particular particle, this antinoe, is always right-handed. It turns out today we know that this has to be the case. Of course, they didn't know at that particular time. But today we know that there is this particle, but Niels Bohr, whose name came up when he was given this kind of information, he actually thought that perhaps in nuclei energy is not conserved, and that's the reason why you have a continuous spectrum. Now in the sphere of ideas, there's nothing wrong with that. Of course, it's a kind of a revolutionary thing to propose, that cornerstone of classical physics, which is that of conservation of energy, something that we all hold as sacrosanct, is actually not true and is violated by, by beta decay, is something that all of us would recoil at. And Pauli also was one who didn't like that idea, and that's how he proposed the neutrino hypothesis. Okay? So today we know that this particular decay is caused by the existence of a vertex like this, where one of the d quarks sitting inside the neutron decays into a u quark with the emission of an electron and an antineutrino. And later, when the muon was discovered, then the muon also was found to decay in the same way with the emission of a new mu like this, with an electron and an antineutrino like this. Okay? So this is the story of the beta decay, which we today know to be maximally, at least this part, which is known as a charged current, actually maximally violates something. Some of my MSc friends violates parity conservation and also, of course, charge conjugation violation, and I'll tell you in a second what these things are. However, the strength of the interaction and the strength of the interaction here are not quite the same, and this has to be modified through something that is known as the Cabibbo angle, which says that there's something happening in the quark sector which doesn't quite happen in the neutrino sector. Okay? And my friend, the S quark that I mentioned earlier, also decays in the same way, like this, with the emission of a U quark with an E minus and a new E bar. But instead of cosine theta c, something known as sine theta c over here, which is the sign of the Cabibbo angle. And this parity violation that we talk about over here, parity violation, is because of the structure of the interaction, which today we call the V minus A structure due to ECG and Marshak and also Feynman and Gell-Mann at roughly the same time, and all this is embedded into something today we call the Glashow-Salam-Weinberg standard model. Later we will see that this actually is not the complete story, because there are more quarks. It's not just the UD and S quarks, but there are also other quarks. And let me just, since I'm here, let me say that you also have the charm and the strange quarks, and the top and the B quarks. Not only that, I'd already mentioned the neutrino and the electron. I'd also mentioned the muon and its. Now we don't want this fellow to feel lonely, so there must be a corresponding members over here. So these muons are leptons. They do not participate in the strong interactions. So the standard model spectrum, so to speak, is made up of these quarks. It's made up of the force carriers. It's made up of the Higgs. And that's it. That's the beautiful theory that we have, which is known as the standard model, where these force carriers are called W plus minus and Z naught along with the photon, and you have the gluons, which are the force carriers of the strong interaction. Not only that, I'm depicting all these by these little points over here to show that these are very, very short range interactions. They are subnuclear interactions, and today we know that such short range interactions are because of the production of virtual particles, which are the force carriers, which are very massive. So if I say that photon, which is massless, is sitting along with W plus minus and Z naught, which are very massive particles, how can it be that you have a massless and massive particles all sitting together? Well, there's a way of making these things massive, and that is known as the Higgs mechanism, which gives masses to these particles. Whereas the gluons are the force carriers of the strong interactions. Okay, so that in short, ladies and gentlemen, is the standard model, everything that you always wanted to know about the standard model, but we're also not afraid to ask, okay, like in the book. So I'm going to ask you and take a momentary break over here, and I'm going to ask you, how can you design an experiment which tells you that the neutrino is actually left-handed? What is the system that you could use? Of course, you have to be able to produce neutrinos, and the way you produce neutrinos is through radioactive decay. You need a nice active radioactive sample that you can use and analyze, and the basic principle behind this was an ingenious experiment to show the handedness, which goes under the name of the Goldhaber experiment. It's a beautiful tabletop experiment that was done in order to establish that the neutrinos are left-handed. It's totally amazing. Okay? So we came across alpha decay, we came across beta decay, and there's one more kind of decay of excited nuclei, and what is that? That is gamma decay. Okay? Now again, the principles of gamma decay are exactly the same as the emission of photons from excited atoms. Now isn't that amazing? I mean, here we are thinking of gamma emission, which is very energetic photons, but the basic laws are still the same, and those are gamma decays of excited nuclei. Let me write this: gamma decays of excited nuclei, also described by the same theory, the same quantum theory as atomic transitions. Now in this regard, there are several interactions that I talked about: weak interaction, electromagnetic interactions, gamma decay, as well as the strong interactions. There's one decay that I've left out so far, and what is that? This was also mentioned by Simon in his talk when he mentioned Chandrasekhar's work. Okay, so what is that? Now Chandrasekhar was interested in stars, and what happens inside stars? Well, they are gravitating objects. See, I let the cat out of the bag. So gravity, right? That's the one force that I didn't mention, and we don't mention it because they're the kinds of energies that we are looking at. Doesn't play a role because it's just flat space that we live in. But if you go to sufficiently high energies, then quantum fluctuations of space-time itself may become important. But still, even at laboratory energies, or let us say at astrophysical energies, it is possible to look at the effects of gravity. For instance, there is such a thing as gravitational redshift, right? Gravitational redshift that all of you are accustomed to hearing when it comes to imaging black holes and all these things. But even terrestrially, it is possible to do gravitational redshift, and there is a gamma ray experiment which employs something known as a Morse-Bauer effect, where radioactive material is embedded in a crystal, and whenever there's an emission of a gamma ray, the entire crystal recoils, and therefore, because the entire crystal is very large, the recoil effect is almost zero. So it's a recoilless decay of a nucleus sitting inside a crystal. And this was used already about 60 years ago to demonstrate gravitational redshift. These are all amazing experiments to read about, gravitational redshift. And this is an experiment that was done by Pound and Rybka. Now, in the copy of the notes that you would get, all the references are given, but I'll also tell you a secret. There are 20 problems given at the end of that scan. So only if you answer those questions, you're allowed to read the rest of the references. Okay? So since we all come from the COVID era, all of us are accustomed to Zoom meetings, we are accustomed to breakout rooms, this and that and the other. So I suggest that students form breakout groups and then they solve these problems together. Or of course you can give it to ChatGPT and ask ChatGPT to solve it for you. Now we have mentioned neutrinos, we've also mentioned photons. Right from the earliest days, everybody is interested in unifying, especially great people like Einstein. They couldn't sleep because there were so many different things. They always wanted to unify things. So the first attempt to unify gravity, since I already mentioned it, gravity plus electromagnetism, was an attempt made by Weil, and I guess at the same time by Klein and who else? Kaluza. All these people had looked at these things. And of course, it was not a successful unification, but Weil's work led to what we call gauge theories, which has a geometric principle, which is the basis of all the standard model physics that we are accustomed to. But what about neutrinos? Now, if Weil could try to unify gravity with electromagnetism, somebody would like to unify neutrinos with something else also, right? And part of this workshop is to present work done in India, and one such very important direction, which again did not work in its original avatar, was an attempt to unify neutrinos with photons. Somebody tell me what this work was? You're trying to unify this. In fact, the name of the paper is The Neutrino Theory of Light, and this was done in IISc by Born and Nath. And while it didn't work in 4 dimensions, it led to an important notion called bosonization, which is used by condensed matter people in 2D to analyze, all kinds of condensed matter systems in a bosonic language. So this is bosonization. Can I take a human interest break over here and tell you a story? How many of you are interested in stories? How many of you are even listening to me? Yeah. Okay, well, Ratan has to listen to me. He has no choice, but nobody else has to. So anyway, some time ago in Bangalore, I had to meet a doctor, and for some reason, nothing serious, and then the doctor, of course, liked to chat. Oh, you're from IISc? I said, yeah. My grandfather used to be at IISc, and then later he went somewhere. I said, is that right? He said, against my advice, my father has given some money to your institute to set up a memorial lecture in his name, and we don't know what happened to that money. Maybe your institute has swallowed it, which is of course possible. Then I said, okay, I'll investigate it, and she was a granddaughter of Nagendranath, and then we managed to dig out that money, and we have established a series of lectures in his memory once in 2 years. So that's the human interest. Okay, was that interesting? Come on, people, how about a round of applause? No? Okay, so that's not the only thing. Neutrinos have always fascinated people, especially people like Murthy. Is he here? Murthy is gone. Okay, so he's supposed to give a talk on neutrinos. There was a paper by Volkov and Akulov where they asked if a neutrino is a Goldstone particle. So this was 1971 or so, and that was essentially the cornerstone of supersymmetry. So this is the idea that they asked, is a neutron a Goldstone particle? Now Goldstone particles arise when certain symmetries break, continuous symmetries break, and because the neutrino is almost a massless particle, they had the idea that perhaps it has something to do with the breakdown of certain space-time symmetry that you may call supersymmetry today. They didn't call it that, but it could very well have been. So much for the neutrino and all its influence on the development of particle physics. Now I want to test a couple of principles more that I have advertised already, especially using some of the particles that I had mentioned. So let us try to return to building and testing the principles such as statistics to build up nuclei. Okay? So nuclei, like atoms, build up. So there's a shell model. So the shells build up. And then you have this idea, in atoms you can imagine that there's a nucleus sitting in the middle, and then there's a first S shell, and there's a P shell, there's a D shell, and so on. Okay? So that's the same idea hold for nuclei. Of course, there's no nucleus in the middle, but it's an effective potential that every nucleon feels because of the presence of the other nucleons. It's an effective potential. And so shells form, and then this forms bigger and bigger nuclei. Okay? So it's the same idea that you want, except that the interactions between nuclei, there's no clear separation as in atomic physics, where you have a fine structure, you have a hyperfine structure, etc. Because there's a hierarchy of scales. Here it doesn't happen because these interactions are fairly strong, and some of the shells that you think ought to be separated are not separated, but actually overlap, and sometimes a shell that you expect should be less energetic becomes more energetic, etc. Those are all the challenges when it came to building up the shell model. But how about testing a basic principle that, in an S shell you cannot put more than 2 particles. Why can you put 2 particles in an S shell? Because there are spins. You can have a spin up and you can have a spin down in an S shell. Okay, but how about trying to test that particular idea? Well, we will use one of the particles that we invented, and we use a particle that's known as a kaon, which is very much like a pion, except that the kaon is a strange meson. It's an S quark and an anti-quark, and let us collide it with a 12 carbon nucleus, and then what happens is that the nucleus here captures the S quark, and then it gives up one of its quarks over here to give a pi minus, which is not strange, and it gives a 12 carbon with a lambda. Okay. Now, how many nucleons does 12 carbon have? Well, it has 12. But how many neutrons and how many protons? 6 and 6. Okay. So let us see how to fill up these. So the 1s shell of the neutrons looks like this. There are 2 sitting in the lowest level, 1, 2, 3, 4. So this is the S shell and this is the P shell, and this can have up to 6, right? Now, what happens in this particular experiment is that you measure the energy of the outgoing pion, okay? The outgoing pion. So then what happens is you kick one of these neutrons out, and instead you get a lambda shell, and then where can the lambda shell start getting occupied? There's only one lambda, okay? Maybe the lambda sits over here. Maybe it also sits here, because now there is no Pauli exclusion principle to actually prevent this from happening, okay? So this is a configuration that can happen where one of where you can get a configuration like this, and you actually beat this Pauli principle, which still has 2 neutrons sitting over here, and in this S shell you also have a lambda, okay? So here is a very beautiful illustration using nuclear physics where you can actually test Pauli principle, okay? So you can do very nice experiments with what are called hypernuclei, because the first name that was given to such particles was that they were called hyperons, because they had, not because they are hyper like me, but because it's just a name that was given, okay? So this is a very beautiful example of testing the Pauli exclusion principle, which is a very basic cornerstone of quantum mechanics, okay? So these are the kinds of ideas that I wanted to mention to you over here as to what are the laws of particle physics that we can test from a very basic and fundamental point of view. Now let me stop here and see if there are any questions for a second. Okay? I had mentioned this word supersymmetry. Now believe it or not, supersymmetry has been discovered long ago, not in the sense that we are accustomed to it, but it was proposed that nuclei, large nuclei that differ only by a half integral spin may actually be related by a symmetry which looks like a supersymmetry. Okay? It's a very kind of quantum mechanical supersymmetry, and this has been observed, and I would like to refer you to an article by Iakello. You can just Google it, on supersymmetry in nuclei. So these ideas are present in so many branches of physics. Of course, they are present in quantum field theory, they are present in superstring theory, etc. But the only place where it has actually been observed in nature is actually in nuclear physics. And when I was doing my preparation for this lecture, and I must confess that it was several days of work preparing for this. In this lecture, in the paper via Kello, he points out that this idea goes back to Miyazawa, long before Akhilov and Volkov, Goldfarb and Lichtman, Wesson-Zumino, who are the people who are often associated with supersymmetry. So Miyazawa had already proposed this in 1966, that there can be such a supersymmetry. Now, ain't that wonderful? Okay. Yeah. And one last thing about, this is not an advertisement for nuclear physics, it's just that it's a basic, many ideas you can understand from nuclear physics is what I'm trying to say, okay? Now, I had already mentioned to you that there is this diagram that I have drawn several times. So this over here was a D quark going to a U quark and an E and a nu E bar, and I had given it a name cosine theta C, which was what Cabibbo had done at a time when only 2 of the flavors of neutrinos and 2 of the flavors of families of quarks were known. So that's the reason why we wrote it only as cosine theta C at that time. But today we don't write it as cosine theta C, but we write it as a certain matrix V and its U D element. Why? Because the D is going into a U, okay? Whereas this other thing here, the S quark. Now somebody has to tell me what is the name that I should give for this matrix element. Somebody. If you don't tell me, then Bala, are you awake? Tell me, what should I call this? No. Okay, he is excused. He is senior to me. So this we would call VUS, like this. Okay. Now there is also one more thing, which would be VUB, where a B quark a B quark can turn into a U quark with an E and a new E bar, and we would call this VUB. Now I want you to tell me why I'm putting this absolute value over here rather than just calling it VUB. Now when I wrote cosine theta C at this time, we assumed that theta is a real angle and cosine theta is also a real number, but it turns out that if you have 3 families of particles, these matrices in general are not real, but they can be complex. But they will not be arbitrarily complex because there are many constraints on such a mixing matrix, and it will turn out that if you have 3 such families, then you end up with 3 mixing angles, and one phase which you cannot eliminate, and this phase leads to what is known as, somebody, let's have a chorus. This leads to CP violation, and this full theory was what is known as Kabibo and Kobayashi and Masukawa. Kabibo, Kobayashi and Masukawa, and of course it led to a Nobel Prize, the first time in the history of humanity where a 3x3 matrix actually led to a Nobel Prize. Okay, but you will find out that tomorrow or one of the later days of this workshop that an analogous mixing matrix also arises in neutrinos, where the number of phases can be larger in the neutrino sector, and I'll just mention it here so that for your future references, and this is called the PMNS, as in Pontecorvo, Corvo, Maki, Nakagawa, Sakata. It's like a rule. All mixing matrices must have one Italian and an arbitrary number of Japanese. Otherwise, you're not qualified to invent mixing matrices. There's no Ravi, there's no Anand mixing matrix. Too bad. Wrong nationality. Huh? Why are you all so serious, folks? It's almost the end of the evening, right? So, now what I wanted to say, so here in principle, depending on whether neutrinos are Dirac or Majorana, whose name you already heard in Subhash's talk, Dirac or Majorana, you can have either 1 or 3 phases. You can have more CP violation in neutrinos than you have with quarks. But that said, what I wanted to say is that the best source of experimental measurement of VUD comes not from elementary particle physics, but from nuclear physics, but in something known as super allowed decays. Super allowed decays. Can anybody tell me what these are? This is not a class in general knowledge. This is something that everybody needs to know. If you're a practicing physicist, you should know that super allowed decays are when a nucleus with 0 plus even decays into a daughter, which is also a super allowed decay 0 plus. It has to decay into something through what are called Fermi transitions alone. Please check this. I didn't have time to check this. Fermi decays only. In contrast to what? So-called Gamow-Teller decays. Okay. Now, I had given you this illustration of the deuteron, where you take magnetic moments of the proton and the neutron and you just add them up and you just get the magnetic moment of the deuteron. Can we do something similar for protons and neutrons that I just mentioned? Can you just take, magnetic moments of 2 up quarks, add it to magnetic moment of a d quark, and just get the magnetic moment of the proton? Is that possible? Okay, that's my question. To some extent it is, except that the proton is a more complicated object, right? It has 2 u quarks. You can't just add things like that. You have to be able to symmetrize and anti-symmetrize these identical particles, and you have to do some algebra in order to get it right. And it turns out that in what we call the quark model, it's possible to do that. So this is my introduction to the quark model for you with UDS quarks. And this model was first introduced, believe it or not, 1961 or so, It was first announced in Bangalore by Gelman, and there's a very nice article by late Professor Rajasekaran in Resonance on the history of this particular discovery. So the idea is to represent these quarks that we already mentioned, D and U quarks, in this isospin axis, and an S quark over here, like this, called as the quark triplet over here in these two axes, because the symmetry associated with this is something called SU3 flavor. So if you have 3 of them, there are 2 mutually diagonal operators. One of them is called the strangeness, other is called the third component, the isospin, and you can draw this like this. On the other hand, the anti-quarks will look like this. There is a U bar like this, there's a D bar like this, and then there's an S bar like this. Okay? So this is called a 3-dimensional representation. This is called a 3-bar representation. And then you can organize the other particles of the spectrum that you know in a plot in this 2-dimensional space. And let me try to do that for you. I have introduced various particles for you, pions, kaons, but the secret is that they can also be organized in a plot like this, and that we can do a little bit of algebra also, if possible, to illustrate some of these ideas. So the states of interest to us are going to be what are called mesons. Somebody remind me, what is a meson? Meson. Somebody, anybody? Yeah. All these people, they haven't taught in many years, they've forgotten. Yeah. Meson is made up of a quark and an anti-quark, so let us call it Q and a Q bar, like that, in contrast to baryons, examples that I've already mentioned. Baryons, which are made up of 3 quarks, 3 similar, same. So one such thing that I can do for you are objects that I already mentioned. So let me draw this here first. Let me call this pion, pi 0 and a pi plus, like this. And then in this, so they have no strangeness, that is why they are lying on this axis. And on the strange axis, I can have more particles like this, and I better get it right. K0, K plus, and then this is a K minus and a K0 bar, like so. But this is only 7, looks very strange. What happened to the 8th one? Well, there's an 8th one. This is called the eta. Not only that, this forms what is called as the pseudo-scalar octet, and it is a JP of 0 minus. Pseudo because this is minus, and scalar because this is a 0. Now this is the ground state. There is no orbital angular momentum associated with these things. The spin is equal to 0. But then there's an excited version of these guys, and this is the JP equals 1 minus. And let's call this a rho minus, let's call this a rho naught, let's call this a rho plus. And let's give names to these, very original names. Let's take a K naught and put a star to show that it is an excited state. Now, all of you will be able to write down the other entries. K star plus, this is a K star minus, K star bar 0, like that. But this is only 7. What happened to the others? Well, there is a phi, which is a resonance in SS bar, and then there is an omega. So the states here are exactly like the states over here, except that this angular momentum is different. The reason why the angular momentum is different is that in the pseudo-scalar octet, the spins are pointing opposite to each other, whereas in the vector, they are pointing in the same direction. But these are typically much heavier than these. Why are they much heavier than this? Now remember that the quarks are like magnets, okay? So these magnets, if you try to line them up, they are going to cost you energy. And this is not just the electromagnetic magnetic field, but it is a chromomagnetic electric field. Chromomagnetic, strong interaction. If it is strongly interacting, costs a lot of energy. That's why the mass splitting is very high. And this is 770 MeV contrasted to 140 MeV. To see how much of chromomagnetic energy is present in this particular state. Okay. Now let me do the same thing for the baryons. Let me try to organize baryons, and I'm sure you won't mind if I do it like this. I write the proton and the neutron like this. Neutron and the proton. There's no strangeness over here. Neutron and proton. 3 quarks over here. Then I had already mentioned the lambda, so let me write the lambda over here. Then there are other cousins of the lambda and yet another cousin over here. And this cousin is called sigma minus, is called a sigma naught, this is called a sigma plus. And these guys over here is called a chi minus and a chi naught like this, capital chi, okay? I'm after something, okay? That's the reason why I'm doing all this for you. And I want to illustrate something. So just as you had these excited cousins of these guys, how about trying to excite these guys also? Now this has a JP of half with a minus. Obviously we know that. It's a spin half particle, and then this is a half plus like this. Now if it is made up of 3 quarks and you try to line up all the 3 quarks, what's the total angular momentum that you can get? You can get JP equal to, somebody tell me, do I hear a chorus? I don't hear anything. 3 halves if you add up, 3 halves, okay. 3 by 2 plus like this, and this gives you 4 states like this, and this is, let's see, 1, 2, 3, 4 like this. So this is a delta minus, delta naught, delta, I think there's something wrong with my axis, it should probably be over here like this, something like this. Okay, this is a delta plus and delta plus plus. And then there are corresponding states like this. And let me again, since we are totally lacking in imagination, let me put it as sigma star with minus, sigma star 0, sigma star plus. Now somebody here has to tell me what this is called. Look at this. Chi star minus chi star 0, but there we have run out of symbols. What shall I put over here? Omega minus, okay? But this is not a dumb plot, okay? Because now this system is where this delta plus plus and these omega minus, they are made up of 3 identical quarks, okay? Not only that, all their spins are pointing up. There is no angular momentum, orbital angular momentum. Then what happens to the Pauli exclusion principle? What happens to the Pauli exclusion principle in this system? My friend there shaking his head. You tell me, what happened to the Pauli exclusion principle? Yeah, black t-shirt and spectacles. You see, otherwise you're all identical. You must be carrying some strange quantum number. Yeah, tell me. Another quantum number which we call color, okay? And the wave function is fully antisymmetric in that color quantum number. But this is not a mathematical construct, although initially it was. Today we know that that is a dynamical freedom, a degree of freedom. It is known as intrinsic color, and it is the basis of quantum chromodynamics, which is present in this bound state system, okay? So we have tested Pauli exclusion principle over here. We have established the existence of a dynamical degree of freedom, which is known as color, and its dynamics needs to be worked out. And what's your number for the number of colors, okay? Looking at this, you may say, oh, it must be just 3 because then I can anti-symmetrize very nicely. But you have to find mathematically that's consistent. But you have to be able to prove it from other experimental observations. And that was a paper that was written by Fritsch, Gell-Mann, and Reutweiler, and it had the very modest title of Advantages of the Color Octet Picture, okay? So that's considered as the foundational paper of QCD. And you establish that the number of colors is equal to 3 by looking at a ratio of E plus E minus to hadrons. The hadrons are all strongly interacting particles, E plus E minus to mu plus mu minus. You also get it from the width of the pi 0 to 2 photons. These are the experimental pieces of information which fix the number of colors to be equal to 3, okay? Now, the mail from Sibashi said, you should try to work out things on the blackboard and show some real calculations. So let's try to do that. Okay. People can stay here until my morning talk also. We can keep talking all the way, right? Take a break for dinner and then reassemble for my morning talk, and I'll be really done. this would be pura paisa vasool for supporting my travel, right? And guest house. No smile from any of you people. You're all kind of collapsing. Huh? Okay. I didn't hear anything. At my age, I don't hear. So anyway, so having done that, now I have argued for you that the mass splitting between these particles and their excited counterpart, these particles and their excited counterpart, is because of the chromomagnetic interaction. So I have already said that this is because of the spin-spin interaction. Let us see how the spin-spin interaction works. So we want to say that it's all because of S1 dot S2 for the case of mesons. So we are saying that this is where this is coming from. And then we said that the total angular momentum is S1 plus S2, and the allowed values of J, total angular momentum, are 0 for Jp equals 0 minus, and equal to 1 for Jp equals 1 minus, right? These are the two possibilities. And I want to calculate what is the energy budget for this S1 dot S2. Now somebody please tell me, how would I get it from this? Where is S1 dot S2 sitting in this particular expression? Anybody? Come on, this is going to be a homework problem. Sitting there, problems 1 to 20. Okay, so what we're going to do is we're going to look at J squared, which is equal to, someone tell me, S1 squared plus S2 squared plus 2 S1 dot S2, right? So S1 dot S2 is equal to J squared minus S1 squared minus S2 squared, right? We know that S1 equals S2 equal to half. So we have to compute it for the two cases of J equals 0 and J equals 1. So what are the eigenvalues of J squared? Eigenvalues of J squared, J times J plus 1. Eigenvalue of S1 squared, S1 times S1 plus 1. Eigenvalues of S1 squared, S2 squared, right? So if you do this, you will straight away get that the mass splitting is minus 3k for L equals 0, or J equals 0 equals plus k for J equals 1. See? So that is the mass splitting. Okay. Now how many of you know an elementary derivation of this J times J plus 1? How many of you know? Okay, anyway, I worked it out. I don't have time to do it, even though I was supposed to do very elementary things. It's not possible. Okay, now for the case of the baryons, what is the corresponding source of the mass splitting? There are three quarks now, S1, S2, S3, right? So what would be the source of the mass splitting? It would be S1 dot S2 plus S2 dot S3 plus S3 dot S1, right? And the total angular momentum J comes from S1 plus S2 plus S3, like this. So again, you can do the same thing, and you can have J squared as Si squared sum plus 2 times S1 dot S2 plus S2 dot S3 plus S3 dot S1. So you can straight away see, you can do the algebra, and then you will see that there's a mass splitting of minus 3k prime for L equals half and plus 3k prime for L equals 3 by 2. Are you all keeping up with me? No problem? Oh, it's very straightforward. These are all the best students in the country, so they should have no problem keeping up with all this. Now I'm going to ask you a question. What do you think is going to be the story of adding up the individual magnetic moments of the quarks to get the magnetic moment of, let's say, the proton or the neutron or the lambda? Okay? It's not just adding up, because there are two U's in one quark or two D's in one U quark, right? So it doesn't quite work that way, but almost. There are some relative Krebs-Gordon coefficients associated with symmetrizing, anti-symmetrizing, etc. But it will turn out that the magnetic moment of the proton is 4 by 3 times magnetic moment of the U quark minus 1 by 3 times magnetic moment of the D quark. Now we already said that Heisenberg said that protons and neutrons are just like each other when you swap U and D quarks. Okay? Now it would be very rude on our part to contradict Heisenberg. So somebody tell me, think of Heisenberg, and tell me what would be the magnetic moment of the neutron. Quick. Quick. 4/3 times mu d minus 1/3 times mu u. Just a swap between the U and D. And turns out that the magnetic moment of the lambda, because the U and S quarks, they just wash out each other, is nothing but the magnetic moment of the S quark. That's the beauty of this quark picture, that despite the very complicated interactions that go on inside the proton, neutron, lambda, etc., this gives a fairly simple picture of how to get these properties. Okay? Now, if you plug in these values in terms of the nuclear magneton and constituent quark mass, etc., mu n divided by mu p is equal to minus 2/3 in the model. Whereas in reality, and this is the number that I had mentioned to you earlier, 1.91 divided by 2.79. Somebody take out your pocket calculator, although I had forbidden the use of electronic devices. Somebody evaluate this and give me the number quickly. Govindarajan, come on. There's a contest. Yeah. Oh, WhatsApp. I thought you were going to calculate this number. What kind of professors do you have, in your institute? Yeah. Yeah. How much? Anybody? You have to speak louder. I told you I can't hear it at my age. 0 point? See? Do you think that's a good number or a bad number? Minus 0.685. Look at the amazing agreement. This is minus 0.67. So this quark model, that is such a, it's a major approximation to what is life. Still, this particular ratio comes out to be very nice. Okay? Now, in case you think that all this has nothing to do with other members of this institute, you're mistaken, because this is the number that enters a very famous line, very important in astrophysics, that is used to track intergalactic medium, etc. And what is that line? Somebody tell me, what is that line? It's a hydrogen line, which is the famous 21.1 centimeter line, which comes from the hyperfine splitting of hydrogen gas. There's this ortho and para hydrogen and that transition, and this was predicted by Van de Hulst, I think in the early 1930s, and it comes from a beautiful splitting which uses very similar formulas like this. There is a splitting between the triplet up here, and then there is the singlet, and this involves that particular number gamma p, and this is equal to 32 gamma p divided by 3p, 3 mass of the proton c squared E1 squared. So this gamma p, I think, is this 2.79 mass of the proton. We already know what it is. And E1, what is E1? E1 is the ionization potential. It's a very famous number, which is 13.6 eV. Mass of the proton is 939 MeV, so that makes it 10 to the power of 6 eV, like so. And gamma p is this 2.79 that we have over here. Then you put in all the conversion factors of h bar c, etc. H bar c. Now you can of course look up the table of fundamental constants, but this is another very useful number to remember, 197 MeV femtometer. Okay, so one of the ideas I wanted to convey in this particular lecture was a lot of what we do, ultimately we have to relate it to numbers. Okay, so in most of the talks of the morning, you had concepts, ideas, concepts, but sometimes you also have to put it into numbers in order to turn this into what you can compare with the real world in terms of cross sections, in terms of hydrogen lines and so on, right? I have 5 more minutes. That's pretty deadly. No, I understand, So let me just, there's one more example that I wanted to do since this scan will be made available to you. I also wanted to introduce this CP violation which I already introduced through the Kabibo-Kobayashi-Masakawa matrix. It shows up in very specific phenomena. For instance, in the system that I discussed today of kaons, neutral kaons can oscillate back and forth. A K0 can go into a K0 bar can come back into a K0. Why is that? Because we already said that the weak interactions can violate strangeness, whereas quark can decay. So it may not decay, but it may produce some particles virtually and then decay into its K0 bar. So in this K0 bar system, which is actually a beautiful application of just basic quantum mechanics oscillation phenomena, this was already studied in the 60s, and experimentally it was discovered in 1964, a very good year. Just keep it in mind, 1964, very good year. It was the Higgs year also. It was also the year of your speakers, but anyway, so of course what makes it the most important here. So anyway, this K0 bar system shows this phenomenon of CP violation. In that, one particular combination is not supposed to decay into 2 pions, but it does at a very small but measurable rate. So up until the beginning of this century, that was the only known example of CP violation, but later with the construction of B factories and so on, we have found CP violation in the B system, which is a far richer system, richer because the B quark is so heavy that it has a large number of final states that it can decay into, and this will be covered by Rahul Sinha in one of his talks later during this workshop. But these B factories also have the possibility of demonstrating many other interesting phenomena such as EPR correlations and things of this sort, and there are also tests proposed of quantum mechanics, violation thereof, dating back to the work of Bell and Steinberger, very important paper they wrote, and many others have followed it up at other E plus C minus machines, Eberhard for instance. There's a review article by D'Ambrosio where he has written about this, and across in TIFR, KVL Sharma, where G.V. Das had worked on this in the 90s. Some of the other things that I wanted to mention of great importance in terms of contributions from India are the Dirac charge quantization condition, which was obviously found by Dirac, was also discussed by Saha in a very important paper where he gave a rather physical derivation where he considers the quantization of the angular momentum field. Okay, and his original paper not that easy to understand in my opinion, but Patrick Dasgupta has some lecture notes available on the internet. It's a part of some other talk that he gave, but he has discussed the angular momentum of the electromagnetic field. There are many other amazing things that one can do with quantum mechanics, combining with particle physics. For instance, there's a recent paper from Grenoble, where Grenoble is a place in France which has reactors, nuclear reactors, but many of those reactors are for laboratory purposes, so you can do very nice experiments with them. So they have ultra cold neutron facilities with which they have studied the quantization of the Earth's magnetic gravitational field. Okay, that's pretty amazing, very delicate. It involves Newton's constant, which, as you know, is an extremely small number. Still, with these ultra cold neutrons, they have been able to propose some ideas, some experiments. And I had a few other examples like this of the interaction of quantum mechanics with gravity, namely the radius of a neutron star, which you can get from basic principles. And for a neutron star of 1.5 solar masses, you can compute through a very pretty formula that involves only the mass of the nucleon and Newton's constant and h bar. Obviously, you can get the radius to be about 12 kilometers. It is in very simplified picture, but nevertheless it gives a reasonably good answer. And there are many other ideas of quantum mechanics which are used, dark matter searches. Haqqani Hamed has given this idea of Sommerfeld enhancement. Some of these things that you can look up, and a few other references that I have given. Neutrino mixing also, I think, is something that you can basically derive from quantum mechanics. It's just more, it's just an application of quantum mechanics in medium with ideas that go back to Landau and Zener, and you have level crossing and these formulas, basic QM ideas. There's also a paper that was written by my retired colleague Pasupati 25 years ago at the time of the 100th anniversary of Planck. He's given a very nice history of the discovery, and also Planck in his original paper had already proposed the various quantities named after him, namely the Planck mass, Planck length, Planck time. You can also combine it with Boltzmann's constant to get a Planck temperature from dimension analysis. So these are all the pretty amazing stuff that one can do with quantum mechanics and try to understand rather complicated things, but by trying to understand from first basic principles where these things are coming from. So as I said, a scan of these notes has been sent to the organizers. So if you're interested, you can ask him, or you can request him to post it on the internet and download it. And the entire flow of ideas is given in this mini poster over here. So some of you are nice to me. I'll give it to you and you can make a copy for yourself. I have a few extra copies also. So let me stop here so that, if I don't tire you out so much that you don't show up for my talk tomorrow morning. So you stop here.
Thanks, Anand, for this very beautiful overview. A particle physicist perspective of how quantum mechanics has been applied to it. Any questions? No questions?
You're exhausted. Yeah. He's my pal. I planted the question. Yeah. Yeah.
In nuclear physics, that supersymmetry which you mentioned.
Yes.
But at the end of the day, it's only softly broken, right? There is no spontaneous breakdown in nuclear physics.
It's a kind of interesting supersymmetry that the excitation spectra of these can be related to each other. Sure. It's just by angular momentum operators you can get this.
Is it used beyond that?
I think there are a few such nuclear systems where this phenomenon is seen. It's reviewed in Yakello, which is already about 25 years old. I don't know what the current status of this topic is. It was around in the 80s when people were still looking at these experiments and this data. Yeah.
Very nice talk. Do you have any comments on some of the developments in the context of entanglement in high energy physics, colliders and things like that?
So the last time I looked at this was from Bell. This was already like 13, 14 years ago, and I wrote an article with a student, Kshitij Garg, which is there in Current Science, where we reviewed. So it was actually the experimental paper itself considers a couple of models as alternatives or extensions of quantum mechanics and does fits and finds that everything is in agreement with quantum mechanics as it should be. In a sense, in all of our particle physics experiments with tagging, things like EPR correlations are somehow manifest. For instance, if you have a B0 bar system, we know that it's oscillating, both sides it's oscillating. So when this thing decays and you see the charge of this, at that instant you have tagged the flavor of this. So to that extent, every measurement, in my opinion, is already EPR correlated. If you want to call that an entanglement, yeah, sure, it is an entanglement. Yeah. Now recently in LHC, they have some TT bar pair production, where again this term entanglement is present, but the paper is too long to read, and so it's given in my list of references. Yeah.
Any other questions? I have a question.
Yeah, sure.
You said about this magnetic moment of lambda.
Yeah.
I did not really follow the argument. You said U and D cancels out. And,
yes.
And if I really look at the spin algebra, it's very similar to nucleon, just that one D is replaced by S.
Yes.
So I did not
really quite, because there's also sigma naught over there. You see, it's a member of the pseudoscalar octet, but there's a sigma minus, sigma naught, and a sigma plus, and the lambda is the kind
it's
of...
actually the okay, so it falls into the antisymmetric part of the flavor segment.
Exactly,
Yes, yes,
exactly.
Yeah, okay.
Yeah. And that's why it is so long-lived, and that is why you can do hypernuclei experiments with lambda and not with the sigma, because the sigma is going to decay. It's all very interesting. I mean, we think of these things as being obvious, not really that obvious, and these are the principles that go into all these experiments.
Maybe one more short
Yeah,
question.
sure.
You talked about neutron, and the next complicated nuclei that you talked was tritium and so triton or so on. Why not dineutron? Why did not?
Dineutron doesn't form, no?
Yeah. What is the reason? Do you have some explanation on?
I don't have any explanation. You lattice people should do it.
If it is diproton, I can argue that it is
there's
actually
a Coulomb
electromagnetic.
repulsion.
But dineutron, I don't know.
There seems to be something to do with the fact that you actually need a proton and a neutron. Maybe it's so loosely bound that that the kind of forces that you need between nucleons is not sufficient to bind it. These are singular nuclear, nuclear forces, as you know, all the experimentalists talk about it. But I don't know what your lattice says about it.
We have several lattice calculations, but not exactly, to my knowledge, not exactly at the physical point.
Okay.
There are these halcuicity calculations that actually try to go through different pion masses.
Yeah.
And they argue that dineutron is repulsive. But these all calculations are done in the isospin symmetric limit, which means dineutron is equivalent to diproton as well.
Yeah.
So I don't know if there is a final answer, but yeah.
So, so when it comes to nucleons, we know that there are two sources for the differences. One is the electromagnetic interaction, and the other is the actual mass difference between the U and D quarks. Now, Feynman and Spiessman, in a half-page article before the quark model, maybe quark model was already there, they looked at the electromagnetic mass splitting. It's another amazing paper that students should look at. It's only one column long, maybe 1.5, where they look at the electromagnetic splitting, and they show that if that's the only source, then the proton has to be heavier than the neutron, which we know is not the case. And therefore, the only resolution is that the D quark is heavier than the U quark. So there are these two things. But how do you disentangle all these things? For you lattice people, it's a big headache for you to be able to, to actually disentangle them and figure out what's what. Whereas in the pion sector, it's the other way. In the pion sector, the neutral pi 0 is 4 MeV lighter than the pions, because there the primary cause is the electromagnetic splitting. And chiral theorems protect the mass of the pions. It's some kind of a quadratic piece in the MD mass difference. So this is what I read. Now, it's not that I have done these calculations myself.
Thanks.
So you mentioned about this kaon scattering on carbon.
Yes. No. Yes.
And then the lambda sitting in the S shell.
Yes.
So what is the consequence of that? I mean, what do
the
we
consequence
observe?
of that is you see a peak in the pion emission spectrum. There is a peak at almost no energy, so that means that it's just going there. Or there's another peak at, I think, about 12 MeV, which means that it is actually occupying the S shell.
I see.
So if you look at the energy distribution, and then you can understand it as the lambda going and sitting in the S shell, which would have been forbidden had it been a neutron. It would have not been allowed. Had it not been non-strange, let's put it this way. So we are saying that if you artificially mark a nucleon with something like an S quark, you can do these interesting experiments. These are all textbook examples, which in a course the teacher will not spend much time on these things, but in this talk I wanted to emphasize for students to think that whatever you're reading in any textbook, there is a hidden principle behind it. That's my philosophy, which I don't know if anybody else shares it.
Where was this experiment done?
These are all in this book of Pov and company, German experimentalists who have written a very nice textbook. So these are all experiments on the 70s, 80s with hypernuclei. Yeah, they've been done in n different places, I'm sure.
Maybe we can move the questions for there is a coffee break, or okay, there is a coffee break, and let's thank both the speakers of the afternoon session, and I hand over to the chair of the workshop.
Yeah, so we'll meet after maybe 15 minutes because we are already running late. So at 5:30 we'll have this panel discussion. basically on this. So today's topic is quantum information science, but it's not just quantum information. It incorporates almost everything in under the name of quantum mechanics, quantum theory. So we can meet together at 5:30, let's say, and then all the speakers of today, I'm requesting all of them to be on the stage, and I'll be there as a moderator.
5:40.
Maybe 5:40.
That is wrong.
Oh, that clock is wrong. Maybe 5:40. Okay. We'll meet at 5:40. Okay. Okay, so it's a bit late, so let's start. As I mentioned, so now we'll have panel discussion with all the 4 speakers, and I'll be there as mere spectator. So we'll talk about, so I invite all the 4 speakers on the stage. I'll call him. So we'll, try to set up the stage to initiate, yes, please, to initiate, some generic discussion in the field of, topic is quantum information science, but as you know, quantum information science is a broad topic. It's not just quantum information computation. I mean, in principle, wherever you can use quantum mechanics effectively and where information is playing the major role, that is something which we have in mind. So the point is that we should have questions or discussions or comments which are generic in nature, not very particular technical question, which I'm not discouraging, but we should have something generic question. And I'm also requesting the audience in the YouTube, if they can write some question on the channel, so that we can also take up those things, those questions. Okay, and why don't you come forward? That will be better.
They are very shy.
Yeah, no, please come forward. Please come forward. Yes. Yeah, that also one can. Yeah, sure. Yeah. Okay. Okay then. Yeah, please come forward. Yeah. Okay, so we have all the 4 speakers of today's session. So Professor Guru Prasad Kaur is telling me that somebody asked him this question about this bell in non-locality. Maybe he will first answer this question, and then we can have general question and comments. Okay. Yeah, you can take this.
Yeah, someone asked me, maybe Govindo Raju or I forgot, whether it is proved that violation of Bell's inequality by quantum mechanics, the amount is 2√2. Then I was answering in a particular way, but it was not proper. Actually, first correlation by operator theory, using operator theory, proved that in quantum mechanics, the Bell quantity which I wrote, that maximum value of this Bell quantity can be 2√2. So it was proved by correlation, that's why it is called correlation bound. But there are other proofs, but if you take just 2 qubits, then just it can be easily proved that the highest amount that Bell quantity can reach is 2√2. For 2 qubits, it is clear, and Horodaki wrote a paper, Horodaki family wrote a paper in 1995, where they did something more. Actually, given any density matrix of 2 qubits, they can show what is the highest amount of Bell violation for that particular state. So for 2 qubits, it is 2√2, but then there are some other proofs of this result in quantum mechanics, including myself, Shivashish. We also proved by using unsharp observable that this amount of Bell violation in quantum mechanics, actually we found amount of Bell violation in a particular no signaling theory, and then and a particular feature of that no signaling theory appeared as a bound on non-locality, and when we put the quantum bound, we derived the quantum bound and we put it, and we saw that this Bell quantity in quantum mechanics can go up to 2 root 2, not beyond that. But what I was trying to tell in that talk, that is there any principle which can tell that 2 root 2 should be the bound given by nature? That was the question first put forward by Popescu and Roddick. And to their surprise, they saw that this no signaling condition does not put any bound. That means you can have a correlation which respects no signaling condition, but at the same time Bell quantity can be 4. That means if you look at the Bell quantity, the highest value of this Bell quantity, algebraic maximum value of this Bell quantity can be 4, and there is no signaling correlation which can attain it at, and I gave you you saw a relation in a table I wrote for which this Bell quantity is 4, and it respects no signaling condition. Then the answer that I was trying to give, whether there is some other principle which can tell that nature should not allow Bell quantity to go beyond 2 root 2. And one such example was put forward maybe in 2010, no? This to the Pawlowski and others. So they suggested a new kind of principle about nature, and it is called information causality principle. But to explain it takes time. But the name is information causality principle, and by using that looks like no signaling principle, but it is stronger than no signaling principle. And using that principle, they could show that Bell quantity by any theory, maybe quantum mechanics may be replaced in future by some other theory, but Bell quantity will be bounded by 2 root 2 if that principle that I am telling about is true. And then there is the result, another result where some scientists showed that if the kind of correlation, that Popescu-Roddick correlation that I was telling about, if that exists in nature, then all this communication complexity problem will be trivial. And this computer scientist does not believe that communication complexity will be trivial, and this Brashad and his collaborator could show it is not that strong like information causality principle, but they showed that if the Bell quantity goes beyond 2.93 or 94, then communication complexity becomes trivial. And they believe that no, nature will not allow this triviality, so Bell quantity should not go beyond that. But that is not exactly 2 root 2, it is 2.93 or 4, something like that. And there are some other principle by which, there is one other principle, macroscopic locality principle, put forward by the name I forgot. They also could derive it is 2 root 2. And people still trying to, there is another principle called local orthogonality principle. They also derived 2 root 2, and maybe in future we will get some other principle which will tell you it is 2 root 2. So more or less all the scientists are of this opinion that most possibly nature gives, this is a bound given by nature. Even quantum mechanics may be replaced by some other theory in future, but this bound will remain. Yeah, that's all. No, information causality can tell that it should not go beyond 2 root 2.
But it has already been observed. 2 root 2 has been demonstrated.
More or less you can, maybe plus minus epsilon, but it is very close to 2 root 2.
So then clearly that argument is not valid.
Which argument?
Whatever objection the computer science people had, that it cannot exceed some...
No, computer scientist is trying, has derived that, so it is 2 root 2 means 2.828. 2.828. some computer scientists could show that if Bell violation goes beyond 2.93 or 94, then communication complexity problem becomes trivial. This needs to be explained actually. So there are some players, you give them inputs, X to Alice, Y to Bob, Z to some other guy, something like that. And they have to calculate a function of all these variables with little communication. And there is the result that if PR Popescu-Broglie correlation exists, then all this communication complexity problem becomes trivial in this sense that just by one bit of communication you can solve all of them. If you have PR correlation, Popescu-Broglie correlation, for which Bell violation is poor.
Yeah, I wanted to ask about your including free will as the third thing, Guru Prasad. You put free will as the, so there was this experiment where they actually made the choice of measurements according to some, I mean human beings were making the choice. It was some large experiment where a lot of people were involved. So but what is the status of that? I mean, will that play any role, or is what do you think? I mean, free will itself.
So when you consider local realistic theory, that means if you create two particles, then it has already predetermined values. Question is whether these predetermined values can influence you to choose a particular type of measurement. If that is assumed, then you can show that Bell's inequality can be violated by 2√2, because then there is a dependence between these two. So you can design things in such a way that Bell violation will be even more than 2√2. So this is an assumption that a experimenter, at least that particularly if they have definite values, those values cannot influence the experimenter to choose a particular measurement setup. So this cannot be proved. This has to be assumed.
Maybe can I comment something on this?
I had one.
Yeah.
In the context of the experiments done by Clauser, Horn and Zeilinger, certainly as from whatever I have read about these experiments, they make sure that there is no possibility of any kind of signal going from the source to the before the photon arrives. Is that and they find, of course, the Bell's inequalities are the results are consistent with Bell's inequalities. Now the question is, these other kinds of notions that you are mentioning, information, causality, etc., are they also, I mean, is one able to also rule out that is this result would also be consistent with this? This information is stronger, information causality requirement is stronger than no signaling. Is that satisfied in an experiment? How do we know?
No, information causality is a principle where communication is needed. So it's just a principle. It has no power to influence the experiment. So it has nothing to do with the experiment. It only tells that Bell violation should not exceed 2√2.
Yeah, maybe I can not about this question, about this, so this Nobel Prize that was given in 2022 to these three people like Clauser and then Alan Aspect and then Anton Zeilinger. So Clauser was one of the first people who came up with this idea, and there will be experiment to verify that Bell violation, I mean Bell inequality violation is there experimentally with cascaded photon. Okay, so because you will have to create some entangled photon source and they are entangled in their polarization degrees of freedom, and that creation of that entangled photon source was not so easy, because that was, I think, 72 or 7, something like that, yeah. So that was not so easy, but anyway he managed to do that. So the time when he did this experiment, so he got violation. Violation means the value of the Bell quantity was more than 2. So therefore it's a violation. Question is how accurate, or in the sense that, I mean, so then people started talking about these loopholes, this locality loophole, then detection loophole, free will, etc., etc. So then, to what extent you can take that result, experimental result of Clauser, okay, that it is actually correct. Because then thereby people could manage to prove that if your detectors, like photon detectors, have, I mean, till now we don't have 100% efficient photodetectors, okay. So if your detectors are not efficient, 100% efficient, and if by some chance there is some leakage of information, like what measurement or measurement statistics is there in one lab to the other lab, then what is the guarantee that whatever you are getting in the experiment through the Bell inequality violation, it is actually showing the Bell violation? And theoretically people figured out that if you have detection inefficiency or some leakage of information from one lab to other lab, then your Bell violation, to show actually Bell violation in that scenario, it will be very, very high, okay. So it is very demanding, and no experiment at that level could show this thing. So primarily there was 2 challenges in this Bell inequality experimental thing. One is the detection loophole. Detection loophole means that your detectors are not 100% efficient. And the other one is locality loophole. So I do some measurement on my system. What is the guarantee that this, the information about this measurement will not influence or will not pass to the other lab, by some means before the other lab starts measuring something, okay. So this locality, this is called, first one is called detection loophole, the other one is called locality loophole. Now, with photons, detection loophole was a great hindrance, because photodetectors are not 100% efficient. In fact, their efficiency is still quite low. I mean, now it has been enhanced. On the other hand, this locality loophole, entangled photons are very good because they don't interact much, okay, and you can take them very, very far apart. So to close detection loophole, entangled photon pairs are good. To close detection loophole, entangled photon pairs are not good, okay. So for that you need like electron spins or something like that, where the detections can be made quite efficiently. So for ages, so Alan Aspect did his first experiment on Bell inequality violation in 1982. Till 2014 or 15, this was a great challenge, that how to come up with one single experiment where both detection loophole and locality loophole can be addressed. And that was done by 3 groups. I forgot their names. One is by Zeilinger, and there are 2 other groups, independently they have done. What they have done, they have taken 2 NV centers, the nitrogen vacancy centers. So there, you probe lasers independently on these NV centers, and there what they do, they create basically, each NV centers, they create entangled electron and photon pairs, okay. And then you take these photon pairs close to a lab, because there you can do these Bell state measurement on the photon pairs, right? And one Bell state, among the 4 Bell state, 1 Bell state measurement is enough, but that will give rise to entanglement in these 2 electrons which are far apart, and this is called entanglement swapping. So using this idea of entanglement swapping, they could manage to produce entanglement between two electrons and which are far apart. So therefore, they can, because electron pairs, if you take them far apart, their entanglement will get lost, unlike photon pairs. So by this swapping process, they could manage to take entangle electron pairs far apart, so that they could do the detection there for Bell violation, and through the swapping, whereby measuring on these two photons, just one Bell state measurement is enough. And this single experiment, by this process, could resolve this detection loophole as well as locality loophole. Now about the free will. So free will tells me that whatever measurement choice I make on my lab is independent of the measurement choice made in the other lab. Okay. So one might say that, let's say that the two experimenters in the two labs are twins. Maybe their mindsets are such that they will fix this thing. So free will says that no, they are completely independent choices. So in that case, these, so the assumption of free will, which of course, one can do statistically. So this Zeilinger, what he has done in his experiment is that he of course took care of this locality and detection loophole, but at the same time, what he has done, choice of this, one of the two measurement, he talked about, Professor Kaur talked about this Bell inequality experiment. One of the two measurement setup you will have to perform on Alice's lab and Bob's lab. The choice of these two measurement was made correlated or connected through some, some astrophysical event, which are very, very far. So these two labs, this choice of measurements have been connected to two different astrophysical events, and they are so far that you can practically think that there cannot be any dependence. So by this way, they basically, I would say practically, came up with this loophole-free, these are the major loophole-free Bell violation experiment. Okay. So maybe I'll, yeah. Yeah. Oh.
The chaos to do with some zeros of zeta function.
Right. Yeah, it's quite a fascinating story. I believe, so the connection of zeros of the zeta function to the two issues of quantum chaos. So for those of you who, just to remind you, there's this Riemann zeta function which is from number theory, and Riemann studied it so that one could understand better the behavior, so to speak, of prime numbers. Things like how many prime numbers are there less than a given number, and so on. So he was trying to find an exact formula for this, and he found out that there is this beautiful function which has a very simple form as a sum, as an infinite series for some variable 1 by n to the power of s. For s larger than 1, and there is analytic continuation for s less than 1, and you can go into the complex plane, and all the zeros of that he conjectured where the non-trivial zeros were lying on a line where the real part is half. So until now this remains an unresolved problem. And if one knows the positions of these zeros on the imaginary, on the half plus I times imaginary line, then one knows a lot about prime numbers. One would know about fluctuations of the prime numbers from some, the density of prime numbers and so on. So for a long time, people, of course, this is one of the holy grails of number theory and mathematics. I believe that this was Montgomery who was studying the Riemann zeta function zeros, and he was looking at 2-point correlations of the zeros on the on this critical line, which means basically like density of the differences between the zeta functions, zeta zeros. So it's like energy levels, we are looking at transitions between energy levels, we are looking at the distributions of these, and so the density of these, and he is looking at the correlations from zeros between the zeros. And the story goes that he was visiting Princeton University and he showed Freeman Dyson the formula for this, which is a nice simple formula. And Freeman Dyson said that's exactly the correlation function for 2-point correlation for random matrices, which he was studying from point of view of nuclear physics at that time, statistical theory of spectra, and for the, in particular, Gaussian unitary ensemble, so time reversal breaking system. So basically just random matrices in which you have Hermitian matrices in which the entries are Gaussian normal distributed. So it seemed like a very remarkable coincidence at that point that these two objects had exactly the same. And then there were these, a lot of, there's this beautiful site of Odlesko who has computed literally zillions of Riemann zeros very accurately, and a lot of numerical work has been done, statistical work on the connections of the of this random matrix to random matrix and the Riemann zeta zeros, looking at the Riemann zeros as if they are eigenvalues of some random matrix. Now the eigenvalues of a random matrix are highly correlated random variables, because you have d square dimensional random variables, you have only d eigenvalues. So they are actually very correlated and a lot is known about them. So people did the reverse, they assumed that this was random matrix, and they derived number theory properties of Riemann zeta function from that. So that is the connection of Riemann zeros to random matrix theory. Now there is this old effort from, I think, Polya and Hilbert probably. They said, okay, we can solve this by finding a Hamiltonian whose eigenvalues will be the Riemann zeta zeros on the critical line. So this was the the chase after. So then I think basically it was Michael Berry who said, okay, now putting together these two facts, that one looks like Gaussian unitary ensemble and we are looking for a Hamiltonian, then what should be the characteristics of that Hamiltonian? It should be something which in the classical limit is chaotic, or in some thing is chaotic, and because it's following random matrix fluctuations so beautifully, and it has to break time reversal symmetry. So then there was this search on, and it is still on, one has not found such a system. But also the other aspect is semi-classical, which I did not go into, which Michael Berry then made very useful connections to. What are the periodic orbits of such a system? What should be the actions of the periodic orbits of such a system, so that you reproduce the Riemann zeta zeros. So it turns out that the actions of such a system's periodic orbits should be going as a log of the prime numbers. And then there are things known about the stability and so on. And then that reproduces formulas known already in number theory. So this connection between the Gutzwiller trace formula, semi-classics, and known formulas in number theory, and then statistical fluctuations of the Riemann zeros versus random matrix theory. So these two are still very tantalizing, and people have had other approaches, very interesting approaches to find this, but it's still a mystery. Yeah. Thanks.
So maybe I can ask Anand. This some of these LHC experiment or other particle physics experiment, they are a very, very high energy level, things are complicated, maybe not cost effective or whatever. So in other branches of physics, people do talk about simulation of experiment with simple-minded quantum system here. So in particle physics, has there been some effort to simulate such experiment in using simple quantum system? Okay.
Well, a lot of what experimentalists do are simulations. There are these major packages like Pythia, Herwig, but those are all like, you're looking for a particular final state and how will it look? Obviously, these systems are so complicated, I don't see how it can correspond to the kind of systems that we are otherwise talking about, not in my understanding. Maybe Ravi has some idea of.
I mean, simulations are very common, as you said, actually.
Yeah.
Before they perform the experiment.
Yeah.
I think this is what they do.
No, in
What I am talking about is, let's say I want to mimic certain properties of some high energy physical system. Certain properties, not all of them. Maybe some spectra or some scattering cross section. So can I think of a simple-minded quantum system where I study this property, which will mimic this?
the only kinds of examples that I can think of are this Bell-Steinberger system that they proposed 1968 or so, and then at a planned factory in the 90s, E plus E minus to kk bar primarily. Frascati is an important machine there called, and the detector was called Chloe, KLOE, KL for K long, and there were many proposals to test quantum mechanics. This Eberhard had a proposal that he wrote. So there are proposals of this kind, either for low energy, not so high energy machines, or for B factories there are proposals. But the LHC is proton on proton, which is an extraordinarily dirty initial state. You can't really do this kind of thing there as far as I can see. At least the initial state has to be clean, which is only possible in E plus E minus collisions, from what I understand. And if you have well-defined resonances, and you know exactly what is the quark content of that resonance, for instance, at Bell experiment, it would be at a resonance called epsilon 4s, 4 for the radial quantum number, S for the shell, which is just has enough energy to decay into BB bar pairs, 2 B meson pairs. And then those are correlated, and there we can test many of these ideas. But and now at LHC they are looking at these TT bar pairs, and this was only announced a few months ago, and where they explicitly talk about quantum entanglement in TT bar production, but I have not been able to read that paper. But it's definitely a topic, at least for a master's student, to see what Atlas and CMS are doing in terms of looking at quantum entanglement at the LHC with TT bar. So it is definitely, in my opinion, a master's project, at least, just to understand what those papers have done and how do they map it to known things.
Can I ask, is there any hope of doing these kind of Bell inequality tests with this entangled pairs? Can you actually?
Those are the questions to be looked at. I don't know.
And also beyond 2 qubits or 2 spin half, are there entanglement? I mean, can you envision, like you have these quarks and this, so would you think of tripartite entanglement and things like that?
Experimentally, this would be very difficult.
But even theoretically, what is kind of?
No idea. These are all, in my opinion, important questions. And
because multipartite entanglement is in fact something which is.
Yeah, these are all topics for the future. I'm sure there are experts discussing this, it's just that I'm not aware of it. I'm sure at CERN they have workshops on these things and people talk about it, but I don't know.
But how are you sure?
Huh?
How are you sure? I'm just kidding.
No, the reason is, whenever you have these machines, millions of dollars, this and that, it is contingent on theorists to test every possible idea. And it doesn't cost anything. This is like a zero cost thing, no? When you just have a small conference, invite local experts, okay. So how to do this and how to take this forward. As I said, this paper by D'Ambrosio, who was a visitor to us, he spent several months with us and got stuck during COVID. And the last evacuation flight of Italy, he managed to get in. He is an expert on these things. But I have not kept up with what he has been doing recently.
Thanks.
I have a question to those who are familiar with quantum computing. See, in particle physics, like Anand said, there are a lot of collisions. And when we compute, some observables like cross sections, we, as a theorist, we write down amplitudes, add them, take the modulus of it, and then do integrals and things like that. That's the kind of steps. Often is computing, the sum of amplitudes. They are quantum amplitudes when they simultaneously all possible configurations, and then you add them. Superposition. And, it's often technically involved. Often computing these things take enormous amount of computing power in normal, classical computers. Are there any ways to compute amplitude? Suppose I give you 100 million amplitudes. Classical computer will fail. Such processes do exist. Processes where so many amplitudes. They are superimposed. Is there a way to compute in quantum using this very sophisticated qubits and things like that? And there is a practical problem that
Actually, there is a lot of computations like all quantum computers, and using quantum Monte Carlo instead of the classical Monte Carlo, there is a contradiction.
coming down. I'm asking not about computing cross sections where you use integrations which involves one.
I see. No,
Oh, okay. So maybe maybe yeah, can be
I'm asking, suppose I compute amplitudes for certain cross section, scattering. Often you get large number of amplitudes, and then for any cross section or observables, we need to add all this, so it's kind of superposition of all of them, and square them and get some observables. But is there a way to, compute this, sum of this amplitude, superposition of this amplitude, using any of this quantum, because quantum computing helps to compute things which are faster than classical one, which is serial. I'm asking.
There are some known tasks for which a quantum computer makes it faster. So I don't know whether in particular this is some, if you reduce it to some mathematical task, I don't know whether it's simply an addition. Then one can ask whether there is an algorithm which will do something faster than a classical one. So at the moment, I don't really understand the nature of the mathematical. Is it just addition or what
It is just addition, like a superposition principle.
Superpositions of states.
Yeah. For example, double slit experiment.
Yeah.
You have two amplitudes and then you add them, square them to get an intensity.
Right.
Okay. It's the same thing that we do in particle physics.
Yeah.
Instead of two amplitudes, it could be many such amplitudes.
Yeah.
I mean, in double slit, you have only two amplitudes. Yeah. But in normal, suppose I collide, like.
But why is it a classically complex task? Is it like going up?
Classically, it's complex because there is, a large number of such terms. In double slit, you have only two amplitudes. You can simply.
Yeah. So it will be going as probably the number of amplitudes which you have.
Exactly.
Its complexity might be n. Are you asking if there is some algorithm which will make it much smaller?
It's also quantum mechanical, so it's more connected to. It's not a classical amplitude.
In a way, yes. So you have a classical superposition, which if you,
maybe I could not understand your question fully, but the point that you are making, that in quantum mechanics amplitude adds, then you take the mod and square it, sometimes it vanish, and
Right.
sometimes it becomes big. That is the thing that induced some physicists to think whether it can be used for faster computing. So in
So I'm
quantum,
asking a reverse engineering actually. Can I solve my problem using this idea actually?
oh,
Large-
then maybe your question is whether you can simulate some quantum mechanical problem by using simpler quantum mechanical system. So maybe Feynman's idea was like that because when you take n qubits, the space is 2 to the power n, 2 power n. So I don't know much about it, but
Maybe I cannot answer your question completely, but let me
No, it
try.
doesn't. There's no
Yeah.
meaning also, but I'm
So
just.
maybe, so there is something called boson sampling. So where you have, let's say, n photons which are coming on interferometers. This is linear process like beam splitter, etc., phase shifter. And then ultimately you have the photodetectors in the end. And you are looking for a particular statistics of the photons there. Now boson sampling is basically looking at these amplitudes, some of these amplitudes, but with a specific property. Okay, not arbitrary sum of amplitude, but with a specific property. And people do believe that it will give you, so if you use quantum computers, it will provide you better, more efficient solution to it. Unfortunately, we still don't have, so theoretically we do understand, yes, it should be, but experimentally we are not in a position to prove this thing, to verify this thing, but theoretically we do understand.
I think it's very much
So-
connected to my
So
question.
this is what is called as, if boson sampling can be shown to be efficient compared to classical one, then this is what we call as an instance of quantum supremacy. Okay. So what you are asking is something of that nature.
Yeah. Okay, thank you.
Now, I have a sort of a comment because sometimes certain terminology is used in the literature which I had found confusing and later on clarified it for myself, and particularly when we're dealing with bosons and fermions. Fermions I'll come to in a second, but when this term of entangled photons is quite used very commonly. So I was a bit confused simply because of the fact that I know that if I have n bosons and the Hilbert space is the symmetrized subspace of this Hilbert space, the moment you do symmetrization, the tensor product structure gets lost. So you cannot talk about entangled bosons in that sense, in the sense in which you can talk about entangled qubits, but because of this symmetrization. However, you can still speak, if you look at the bosonic space from the point of view of Fock description, then you can speak of entangled modes. Entanglement between modes, because the full Fock space containing can be thought of as a tensor product of Hilbert spaces, one for each mode, much the same way as you can talk about qubits described by each Hilbert space. So when one speaks of two photon entanglement, one should probably remember that what one has in mind is entanglement between two modes or three modes populated by two photons or three photons, because otherwise this terminology confuses, at least confused me, so I thought I'll brought it to your attention. Now when we come, now there is a question which bothers me and troubles me quite a lot. This is as far as the bosons are concerned. But the moment you go to fermions, then if you look at even again, similarly, you follow the steps as you do for the bosons, then you construct a Fock space, but the operators belonging to, let's say, let me continue to use the term mode or possible single particle energies, they anti-commute. So the Fock space cannot be thought of as a tensor product in any sense. And that's where I get confused when in condensed matter physics this word is used quite often, fermionic entanglement, etc. I do not know in what sense is that to be understood. So those who are more knowledgeable in condensed matter physics than I am can perhaps clarify what is meant by entanglement between electrons, for instance. Because the Fock space does not have a tensor product structure at all in any sense. So maybe Arul, you are probably better qualified to answer this question.
No, this is a difficult question. So, because yes, all identical particles, not just certainly for fermions and more generally anyons and all the fractional statistics, which I think all of them have this particular problem that already there is an entanglement because of symmetry. So, right? I mean, from the point of view of, let's say you have just 2 electrons, and then you would already have an antisymmetric superposition.
We have gone to the Fock description.
Yeah.
And we have a
Yeah.
polynomial of creation operator.
Yeah. Yeah.
I have this Fock space.
Right. So there are some approaches which I'm familiar with, but I have not used it myself. So one is to actually kind of factor this out. So from the point of, if you look at fermions, all the Slater determinants, they are, you have to factor out the entanglement which is coming from this, and actually only take the interaction, the entanglement which is coming from interactions rather than symmetry. So there is some amount of work on this, but I'm not really an expert. From point of view of, let's say, something like many body localization, where one is still talking about fermions and but spin half particles, mostly all of these things are probably not, because I don't know, maybe again I could be wrong, but just localization when one talks about that. And one is talking about localization in Fock space as far as this many body localization. But if you just consider Anderson localization, that's really localization in space. So when one is doing that, one has already in some sense, lost that. I mean, you have already identified some electrons as being here versus there. So, okay, I think Subhashish has actually thought more about this and has even worked on it. So I'll pass the hot cake to him.
No, I mean, yes, it is true that in the case of indistinguishable particles, be it bosons or fermions or even anyons, talking about entanglement is a tricky issue because we don't have this tensor product structure there. So, so there are these notions called particle entanglement and mode entanglement. So mode entanglement, of course, we know.
Bosons, fine.
Right. Even for fermions also one can talk about mode entanglement. So
No, that is where my question is, that if I look at the Fock space as consisting of monomials in A1 dagger, A2 dagger, etc., acting on the vacuum state. Now A1 dagger, if I associate it with mode number 1, A2 dagger with mode number 2, but these operators anti-commute with each other. So there is no tensor product much in the sense that we have in the context of bosons, where we can talk about, if you look at it from mode point of view, then the Hilbert space has a tensor product structure. But because here the operators corresponding to different modes anti-commute, I cannot think of it as a tensor product.
No, you don't have to think about tensor product. So the question is that operationally, if you have, let's say, n mode fermions, I mean, not n fermions, n mode fermions. Fermions can be there n or less than n. So then, can I divide these n mode fermions into two groups? Let's say k mode fermions, n minus k modes. So that, I can have access to these k modes and somebody else has access to the n minus k mode. So maybe one can think of like orbitals of, some atoms. So one orbital or maybe a bunch of orbitals will give rise to this k set of modes and the rest of them will give rise to the remaining modes. So that if I can address, and that is possible, that is not impossible, then it makes sense even for fermions to have mode entanglement there. At least this is my understanding goes. And particle entanglement is just like what we understand in the case.
No,
Yeah.
I was happy with, bosons was your. So my confusion is basically that one is going beyond the definition of entanglement as we understand, as we emphasize that we have a tensor product of Hilbert spaces, one for each subsystem, and then you can have separable states and entangled states. I am not able to reconcile this picture in the context of fermions. Maybe I can speak to you later.
Yeah, and no, I just wanted to remind people that maybe a better way to state this is in terms of the Schmidt decomposition. So right in the Schmidt decomposition, we always take a product of the individual systems and then you have this Schmidt matrix which you do the singular value decomposition, etc. And you get the rank, and if the Schmidt rank is greater than 2, you say equal to or greater than 2, you say it is entangled otherwise. So people have written down for indistinguishable particles, instead of using simply a direct product of the individual particles, you have to symmetrize or anti-symmetrize, just like use Hartree or Hartree-Fock wave functions, in fact Slater determination. And then so you can define something called the Slater rank, just like the Schmidt rank.
Yes, yes.
And if that happens to be greater than 2,
Yes.
then it is genuinely entangled.
Yes.
So in some sense, like Arul was saying, you have factored out the quantum, the entanglement coming through because of quantum statistics has to be factored out, and then you talk about the other entanglement.
No, what you say is right. I mean, that is automatically, the anti-symmetrization is automatically taken care of by the algebra of creation and annihilation operators. So I don't worry about it. I look at the Fock space. I have a certain monomial in the creation operators acting on 0, and all possible, such collection of all such possibilities gives me the Fock space. Now, in this Fock space, A1 acting on the first mode anti-commutes with A2. So I can't think of A1 as acting on one Hilbert space, because operators acting on different Hilbert spaces in the tensor product should commute with each other. So if they anti-commute, then I don't have that structure. All right. Now this question of Slater determinant, there was this paper some time ago based on, I mean, in normal courses in quantum entanglement that we teach, we start with the conventional definition of entanglement, and then Schmidt decomposition. You want to find out what is the minimum number of terms that are required in order to express this vector, and then you would decide whether the Schmidt rank is higher than 1, you say it's a product state. If it is higher than 1, it's an entangled state. If it is 1, it is a product state. Fine. But all this is starting from the definition of entanglement, where the Hilbert space describing the composite system is a tensor product of the constituent subsystems. In the case of fermions, I am not able to reconcile that picture. What you say is that forget about the definition of entanglement, start with the Schmidt decomposition of that in terms of And this is some work done by Dagmar Bruce and a whole lot of others. Dagmar Bruce and a whole lot of others. But there, if you look at the paper carefully, then if I have got, say for example, capital N fermions, and I want to ask the question whether one fermion is coupled with the rest, some question of that kind. You have to do enormous amount of work. I mean, tracing, and suppose you have n to equal to 10 to the 23, and if I want to find out whether one electron is entangled with the rest, the amount of effort to deduce it from the given state is enormous. So I don't know whether that is a good definition, and is that definition actually followed by people who say that they talk about fermionic entanglement in condensed matter physics systems. I don't know.
Yeah, I mean, once it is a fermion and if you have 10 to the 23 particles, it has to be antisymmetric with respect to every one of them.
Anyway, all I want to say is that this is some question which I think some of you should perhaps look at and examine it and come up. Maybe one doesn't have to stick to the original definition of entanglement, but you can't avoid that because that is a part of quantum mechanics, that composite systems are to be described in this manner. So one has to, again, in the case of bosons, for instance, we can think of the given quantized radiation field as consisting not of particles but of describing certain number of modes. And that is our starting point. Then we can reconcile it with the conventional definition of entanglement. But in the case of fermions, I am not very clear whether such a picture holds or...
Can I say something about this? So basically, there is nothing sacrosanct about this tensor product structure for dealing with entanglement. So the question is that when you talk about that operators of one Hilbert space should commute with operators of other Hilbert space when you take tensor product, yes, that is true. We should think about it operationally. So the question is that can I measure a set of operators jointly? Okay. So whenever I can measure these, maybe two operators, can I measure them jointly? So then, I can of course say that I can assign values to this operator, I can assign values to the operators simultaneously. There is no issue with that. So rather than, assigning this commuting structure of operators corresponding to tensor product structure, I would say we should think about operationally, because, nature does not know what is Hilbert space and all those things. So we'll have to think about operationally that when do we consider observables to commute, in the sense of can we measure them simultaneously. Okay. So from that perspective, if we try to address this problem, then we don't have to invoke always this tensor product structure.
I think there was a paper, perhaps Laflamme was involved in it, I don't know, where the effort was made to define entanglement based on the measurable quantities that you can talk about it. But it's just that I do not know of a satisfactory definition based on the algebra of operators on the Hilbert space associated with a composite system that defines a more general notion of entanglement which subsumes the conventional definition of description of a composite system. And it will be very helpful if you can give some reference where this question is discussed.
No, I understand this your concern, but I think in the literature people are trying to address this thing. I'm not saying this has been resolved completely, but people are trying to address. There are different ways of understanding entanglement in the case of fermions. Okay. One approach is what condensed matter physicists do, the second quantization language, because we think that already takes into account this problem, this antisymmetrization and all that.
Yeah, that's where my
That is where one.
dagger
Yeah.
and A2 dagger anti-commute. In the boson case, they commute, so you can say that A1 is associated with mode 1, A2 is associated with mode 2, and operators on these Hilbert spaces associated with each mode are they commute with each other. But in the case of fermions, they anti-commute. So either you define a new tensor product structure, which allows you to also include fermions. I don't know whether there are such.
Yeah, there are certain efforts. So something what is known as wedge product or something, but that's a mathematical thing. But question is operationally whether it can be addressed. I think people have addressed that.
I would be
independently of some measurement performed on the other electron, whether it can be done. Yeah, that's why I am thinking that then there may be entanglement, there may not be entanglement, but what prevents me to perform some spin measurement on this electron according to my own wish and another spin measurement on the other electron. So
what we are looking at.
No, I am coming to this operational question. If that operationally you see, but question of commutating.
I agree with you, because if I imagine that the two electrons were together, then I would say that the corresponding operators anti-commute. And if they move far away, one in one room and another room, I would say now they are distinguishable, and the operators commute with. I mean, I am confused.
Yeah, maybe we can discuss this later. If let us see if any other question.
Just a clarification. So maybe what you discussed today regarding the periphase.
Yes.
You're talking about quantum mechanical systems.
Yes.
Do we see periphases in quantum field theoretic systems?
In a field theoretic setting, I think it will be. I have not looked at it, but certainly it should be possible. Wherever you have, I mean, in a field theory setting, to the extent field theory that I had learned in my younger days, and also worked on Yang-Mills fields and so on, was that, I mean, of course, in quantum field theory you have to, I am sort of more familiar with the LSZ formalism, in which you have Hilbert spaces associated with in states and out states and so on. So I think as far as the definition of the geometric phase is concerned, it is should be, how would it manifest it in a quantum field theory description, I do not know.
So I was coming at it from a different perspective. So there is something called the conformal field theories.
Yes.
Where there is a state and an operator correspondence.
Right.
And the way you presented geometric phase is like a nice structure on the Hilbert space, independent of the dynamics.
Yes.
So the question interesting, maybe it could be interesting, would be what is the corresponding structure in the operator algebra? That
Let me say, at this point I am not able to answer your question.
No, I'm just giving a remark.
Okay, sorry, not exactly an answer to your question, but not exactly a response to the answer that you gave to your question, but to the original question. So I think the problem is the moment we go from quantum mechanics to quantum field theory, we quickly switch to the Heisenberg picture. We do most of our quantum field theory in Heisenberg picture, whereas all this discussion about geometric phases, we use wave functions and stuff like that, essentially in the Schrodinger picture. And then when we go to gauge theories, we quickly pass to path integrals and everything becomes, just doing some integration over classical fields and so on. So I think, but however, there is something which is very well known, which is not as well known as it should be. There's something called the Schrodinger picture of quantum field theory, which essentially mimics quantum mechanics. For example, you have a Schrodinger equation in quantum mechanics, so there is exactly a Schrodinger equation for fields in the Schrodinger picture. The wave function, obviously, coordinates are replaced by fields, because you have gone to quantum field theory, the wave function is replaced by wave functional. But there is a functional analog of the Schrodinger equation. And that may be the right context. If one can do exactly what one does with Schrodinger equation and see how the wave functional evolves when you take it around a circuit in theory space and try to find an analog of the geometric phase. Subhash, now I think you can comment now.
Well, what I would like to say, add a comment here, that in the picture that Mukunda and Simon have developed, it is at a kinetic level. It's a kinematic description. It's not connected with dynamics at all, or Schrodinger equation and so on. So I think to the extent I understand, wherever you have analogs of what we have looked at, and I mean we are looking at quantum mechanics and we have a definition of how to describe the state of a quantum system, which is given by rank 1 projection operators on this Hilbert space. As long as you have this structure, all these considerations certainly apply. Maybe with some appropriate extensions in the context of the problem that you are looking at. This would be my answer.
For instance, neutrino oscillation or kaon, anti-kaon oscillation. Do they have any analog to, Berry phase, or is that completely?
I do not know.
Even that is a cyclic, as a propagation, they oscillate.
There is this work, again in the context of particle physics, as he had talked about CK, Kabibo, Kobayashi, Mascava matrix. And there essentially you have to deal with unitary matrix with certain phases that can be removed from the left and something can be removed from the right. And there's a lot of papers on parametrization of these Kabibo, Mascava, Kabibo, Kobayashi.
Yeah, I guess I'm not asking about the phases involved there, but really the oscillation itself. If you take a kaon, anti-kaon, it's a two-state system and they oscillate between them. Is that analogous to, Berry oscillation, or is that completely?
Yes. The statement that I was trying to make was the following. I can't answer your question very precisely. Was that objects like, if you look at parametrization of these SUN matrices with the possibility of removing the phases from the left and from the right, then these Bargmann type 4-vertex Bargmann invariants appear very naturally, which are invariant under these transformations of removing phases from the left or right. Whether that can in that context be connected with geometric phase, I have no idea.
No, I was asking more directly whether neutrino oscillation itself is a, a quantum field theory manifestation of Berry oscillation in quantum.
No, neutrino oscillations are basically a quantum mechanical problem of two levels
Yeah.
system subject to say, these are it's simply that. These are
Okay.
not.
So then
Can I say something
that's
here?
the corresponding.
Can I say something? So basically, these neutrino oscillation, people have been trying, maybe you know better than me, so people have been trying it to connect it with this, correlation in time, like features of quantum mechanics, which is known as this Leggett-Garg inequality. So you prepare your system, maybe in some particular state, and then you evolve it, so which is in this case this oscillatory behavior. Then you perform measurement, you figure out what are the modes. Then again you evolve it, then you perform measurement, and then you look at, let's say, 3-time measurement correlation. So then it may give rise to this so-called this violation of this Leggett-Garg inequality, and that gives rise to sometimes this quantum nature of, because neutrino oscillation is is a particularly quantum nature. So that is a way of I would say is a kind of manifestation of this quantum feature of neutrino oscillation.
But nothing to do with Berry phase, right?
I don't think so.
Okay.
The assumption that is done for this Leggett-Garg inequality is macroscopic realism.
Yeah, that has to be satisfied, yes.
I'm sorry, I'm posing one more question which troubles me quite a lot. Again, in the context of condensed matter physics, there are many statements to the effect that Berry phase plays this role, particularly in two-dimensional systems. Berry phase is very important, and I have never understood what is the connection between the geometric phase, or as we have understood it here, where the phase is associated with a closed curve in the state space. In the condensed matter context, what happens is that you have a certain integral going from, particularly in two-dimensional system, going from one end of the Brillouin zone to the other end, and that integral turns out to have some significance in these systems, and perhaps the quantity that is being integrated has the structure of the second term that I wrote down in the expression for the geometric phase. And I cannot connect this picture with any kind of a closed curve in state space, which is what, or open curve or whatever in the state space, and say that this is a manifestation of Berry phase. I have not, maybe there's some confusion in the terminology which is confusing me, but if someone with condensed matter physics background who has worked on, say for example, there are claims that in quantum Hall effect also this has an important role, the Berry phase, but I have not been able to make a connection between what they see and the definition that I am familiar with.
Oh, sorry. So any question, any answer from the audience? Or maybe today we don't have many condensed matter physicists here. We are expecting tomorrow or maybe day after tomorrow, but you will be leaving, right? So you will be here only. So maybe we can raise this question to the condensed matter physicist. That will be okay. So actually, I wanted to ask, to all of you this question, but I don't know this. We don't have time now. So the question is that, in quantum information we talk about, not just quantum information, classical information also, we talk about storage of information, processing of information, and then transmission of information. This is true for any information processing, be it quantum or classical. Now there are approaches to understand different physical phenomena using information theoretic language, so like I know this work by someone from Netherlands, where he could manage to show that Newtonian gravity is an emerging phenomena starting from quantum information, something like that, Verlinde, yes. So the question is that if I look for real understanding of quantum information, can one identify or at least characterize what are the emergent phenomena in physics, for example, which can come from from the understanding of quantum information theory? This is one example. So do we have some such understanding? We don't have to discuss now this, maybe we can have.
Are you suggesting that just like gravity, all the other forces?
Yeah, perhaps, yes.
Something about entanglement and space-time itself.
Yes.
I mean, whether Bell inequality violations are somehow connected to.
Yeah, some such thing.
Space-time
Like,
structure.
in condensed matter, we understand that some of these phase transitions, we can understand in terms of this entanglement, multi-party entanglement and all that, their behavior.
Here, Shivashi, a question that we all know that if you have a tensor product of two Hilbert spaces and take an arbitrary vector, the chances are that it will be entangled. So entanglement is generic, whereas a product state is special. So I do not know whether one should attribute everything to entanglement, because it is from a mathematical point of view at least, it is generic.
No, I'm not talking about that. Of course, entanglement is generic. My point is that, can one understand a different phenomena in physics, for example, not just physics, it can be some biological system, whatever. So, starting from the, basics of quantum information, can I say, for example, can I derive, statistical mechanics from quantum information theory? Okay. So, yeah, that is one aspect, yes. So these are the kind of things which maybe we can think about. Okay. So I think if there is no more question, let us end this session, and let me thank all the speakers and also the audience.